Good morning, students. We'll start with the today's lecture. Okay, in the previous lecture, we have started with the root locus techniques chapter, and a brief introduction to root locus was told to you people. Then I have introduced the angle and magnitude condition. If you know that if the angle condition is satisfied, means the point is on the root locus, right? If the point has to be on the root locus, then it has to satisfy the angle condition. Then we make use of the magnitude condition in order to determine the value of k, right? If the point satisfies magnitude condition, doesn't mean that it is on the root locus. But if the point satisfies angle condition, then that point has to be on the root locus, right? And we use magnitude condition to determine the system gain k. Then another method in order to determine the value of k is graphical method that we have seen. K is equal to P1, P2 divided by Z1, Z2 and so on, right? Product of phasor lengths of poles and zeros that we have seen. Then how to construct the root locus. There are set of 8 rules are there, out of which we have covered 5 rules, right? So today we'll be seeing rule number 6, 7, 8. But rule number 1, let me briefly summarize you people. Rule number 1 tells that the root locus is symmetrical about the real axis. It is symmetrical about real axis, right? Symmetrical about real axis. Then rule number 2, it speaks about the branches. It gives information about branches. Right? There are three cases: p greater than z, p less than z, p equal to z, right? So how many number of branches are there, from where they will start, where they will terminate, all those information will be given by rule number 2. Then rule number 3, existence of root locus on real axis. Existence of root locus on real axis. Means in which section on the real axis the root locus exists, right? Then rule number 4 speaks about the asymptotes. These asymptotes are nothing but the guidelines for the branches which are moving towards infinity. And angle of asymptote theta is equal to 2q plus 1 into 180 degree divided by p minus z, that we have seen, right? Then rule number 5, it speaks about centroid. Then we have to locate this asymptotes, right? So the centroid is located on the real axis, right? So it will give the exact location of the asymptotes on the real axis, right? And centroid is denoted by sigma, the formula sigma, and it is equal to sum of real parts of poles minus sum of real parts of zeros divided by p minus z. Okay, we have seen all these 5 rules. Then we will see the rule numbers, remaining rules 6, 7, 8, and we'll solve the numericals on root locus. Is it fine? Okay, rule number 6, it speaks about the breakaway point. What is breakaway point? I will tell you. You can observe here. Just I'll take one example here. This example, this is a common example I am taking for explaining the concept for you people. You can observe here, from this pole, the root locus is coming here, the branch is living here, and it is coming at this point. From this, it is coming here, and it is coming at this point, right? And they are living. One of the branch is living above, and another branch is coming down, right? Okay, this point we call it as breakaway point. Okay, how to define it, I will tell you. This breakaway point, this point is called as breakaway point. Here the breakaway point in this example is minus 0.4514, right? It is having some location here. So what is breakaway point, I will tell you, right? Okay, we will define what is breakaway point. Breakaway point is a point on the root locus where multiple roots of the characteristic equation occurs. For example, I have g of s into h of s. This is the open loop transfer function. We know how to do the characteristic equation. 1 plus g of s into h of s equal to 0. I will get some second order equation, right? So from this, if I substitute g of s, h of, I will get second order equation. Okay. K is varying from 0 to infinity. For k equal to 0, if I solve the roots of this characteristic equation, for k equal to 0, one of the root is 0 and another root is minus 2. Similarly, for k equal to 1, k equal to 0, these are the two roots, 0 and minus 2. For k equal to 1, the roots are same, multiple roots, minus 1 and minus 1. So this we call it as breakaway point. Means breakaway point is a point on the root locus where multiple roots of the characteristic equation occurs for particular value of k. For example, here for this second order equation, for k equal to 1, the multiple roots exist, means -1, -1. These are the multiple roots, right? For particular values of k. Okay, this we call it as breakaway point. For k equal to infinity, we are getting two different roots. But for particular value of k, multiple roots exist. That point we call it as breakaway point. Is it fine? And how to determine that breakaway point? Here, for example, in this example, breakaway point is minus. How to get this breakaway point? We'll see this, right? There are set of rules are there. Okay, and then one more thing, breakaway point. You can see here, always the branches will start from poles. Yes, so branch will start and to come here at this breakaway point. It will start here, and how they are departing at an angle of plus or minus 180 degree divided by n. Plus or minus 180 degree. What is this n? This is the breakaway point. How many branches are approaching this breakaway point? This is one branch and this is two branches. So here n is equal to 2. So plus or minus 180 degree. So the number of branches approaching this breakaway point is 2. So plus or minus, sorry, plus or minus. So plus or minus 90 degree. 180 by 2 is 90 degree. So one of the branch will leave at plus 90 degree and another branch will leave at minus 90 degree. Right? So one branch will live at plus 90 and another branch minus 90, and remaining it proceeds parallel to the asymptote. Asymptote is a guideline, right? This is on asymptote. It tells move parallel with me. Initially at this point, how they will depart? They will depart at an angle of plus 90 and minus 90, and it is given by this formula, plus or minus 180 degree divided by n, and this n tells the number of branches approaching this breakaway point. There are two branches here. This is one branch and this is one branch, right? Okay, the same thing has been told here. That is plus or minus 180 degree divided by n, right? Okay, I hope you understood this. If any doubts, please unmute yourself and talk to me so that I can clarify your doubts. Okay, here there are some general predictions, means where the breakaway point exists. There are three cases here, right? We'll try to understand these three cases. Suppose I have the S plane, sigma and j omega. This is the S plane, right? If there are two adjacently placed poles, let me take these two are adjacently placed. This is at -1, -2. These are we call them as adjacently placed poles because in between them there are no zeros or any other complex conjugate poles. These are adjacently placed poles, right? Okay. Suppose 0 to -1, it is not a part of root locus. Let me assume that 0 to -1 is a part of -1 to -2. This is a part of root locus. Means root locus exists. Let me assume the root locus exists here. Then -1 to -2 section is the root locus and they are adjacently placed poles. So one of the minimum breakaway point exists in this section -1 to 1. Minimum breakaway point exists. Minimum BAP I will write. Breakaway point. Breakaway point means BAP. In short form I am using. Breakaway point exists. Right? Okay. The same thing has been depicted in this picture. Right? Okay. The next, we will see this example. For g of s into h of s equal to k divided k into s plus 6 divided s into s plus 2 s plus 2. How many minimum breakaway point exists? Yes, we will look at all this. So how many poles are located? S equal to 0, -2, -4. Okay, 0, one pole is located. -2, one pole is located. -4. Then s equal to -6 is 0. So here it is located. You can observe here the poles s equal to 0 and -2. These are adjacently placed poles, right? These are adjacently placed poles and the root locus exists between them. You can observe here whether the root locus is there or not. If I consider one point here, to the right of it odd number, s means 0 to -2 is a part of root locus. Then -2 and -4, these are also adjacently placed poles. If I take one point here to the right of it, if I count, two poles are there. Even means -2 to -4, there is no root locus. So there is no question of existence of breakaway point here. Right? So these two are adjacently placed poles and it is a part of the root locus. Hence, one minimum breakaway point exists. I hope you are getting right. This is the one minimum breakaway point that exists between the section 0 to -2 because it's a part of root locus. These two are adjacently placed poles, -2 and -4, but this is not a root locus, no root locus. Hence, no question of breakaway point, right? So this is first case is over, right? Two adjacently placed poles on real axis. Next, we are predicting how many minimum breakaway points exist. Second prediction, if there are adjacently placed zeros, just like adjacently placed poles, adjacently placed zeros. Suppose I have one zero at I have one zero at -2 and I have 0 at -3. These two are adjacently placed 0, and if it's a part of root locus, means let me assume that root locus exists between section, then at least one minimum breakaway point exists between them. One minimum breakaway point exists. Okay, let me take this example. For g of s into h of s equal to k into s plus 2 into s plus 4, s square into s plus 6, how many minimum breakaway point exists? Locate all the poles. S square equal to 0. Two zero poles are located. S square equal to, they are located, right? Then s equal to -6. S, here the pole is located. Then zeros are located -2 and -4. So -2 is 1, -4. These zeros are located. And we know how to find out the root locus existence on real axis. 0 to -2, if I take one point, to the right of it even number of poles are there, so this is not a part of root locus. -2 to -4, let me check it, right? So if I take one point here, to the right of it 1 2 3, yes, this is a root locus exists. Means -2 to -4, the root locus exists here in this section. There is no root locus in this section. If I take from -4 to -6, there is no root locus. From -6, if I take one point here, 1 2 3 4 5, means this, there is a root locus here also from -6 to infinity. But here we will concentrate on two adjacently placed zeros. So -2 -4, these two are adjacently placed zeros, and it is a part of the root locus. Hence one minimum breakaway point exists between them, right? That point can be located anywhere from -2 to -4. I can take it anywhere. And you can observe the direction of arrow mark. Always the branches will approach the zeros. So the arrow mark is free. From this point it is going towards this zero. From this point it is going towards this zero. In the previous case you can observe here, for this is the breakaway point. So always the branches will start from the poles. So from this pole it is coming to breakaway point. From this pole it is coming to this breakaway point. Always the branches will leave the poles and come towards the zeros. You can observe here, from this point it is going towards 0, right? You can observe the arrow mark also here. Is it fine? Branches will always start from open loop poles and they will terminate on the available zeros. So they are terminating, going and terminating on the available zeros. Please keep in the mind. Then third prediction. Okay, this I will tell you before like it. Okay, sigma j omega. I have, let me take one pole is here, another 0 is here, one more pole is here, and lastly one 0 is here. Okay, let me take 0, -1, -2, -5, something like this. Okay, what I am interested only in the 0 which is located at the extreme left. So this 0, right? Not the pole, only 0. So this 0 is located at extreme left as compared to the other poles and zeros. Located at 0, -1, -2. To the left of this extreme 0, there should not be any other poles and zeros. Is there any other poles and zeros in this area? No, right? So this is the extreme 0 towards the left, and it is a, let me assume that this is a part of the root locus. Means let me assume this is a part of the root locus. Means from -5 to infinity, -5 to infinity, the root locus exists, let me assume, right? Then there exists one minimum breakaway point. It can be anywhere. One minimum breakaway point exists. One minimum breakaway point exists. So we can predict how the breakaway point exists. One, two adjacently placed poles and as one minimum breakaway points. Next, second prediction is two adjacently placed zeros. Third one is extreme left 0 and is a part of root, one minimum breakaway point exists. Right? We can predict like this. The same thing, extreme left 0 is this. Right? To the left of it, none of the poles and zeros are there and is a part of the root locus, and one minimum breakaway point exists here. The same thing has been told here. Right? Okay. Yeah, I hope you understood. Then how to determine? Yes, we have predicted. Yes, breakaway point exists. But what? How to calculate this? Right? Exactly where it comes. Right? So that we have to calculate. We have calculated. Right? Here it is coming. What exactly the point? We have to calculate this. So determination of breakaway point. The steps are as follows. First, construct the characteristic equation 1 plus g of s into h of s equal to 0. This is one thing. Yes, we will construct it. After constructing, separate out s terms one side, k term one side, right? K is equal to all the functions of s. S terms one side and separate s terms one side and k terms one side. Then differentiate the above equation with respect to x and equate it to 0, means dk by ds equal to 0. And solve the equation of whatever we got the derivative after taking derivative. Solve that equation, that will give the breakaway point. Okay, I will get some breakaway points. Whether it is valid or not, that I have to tell. Whether that breakaway point is valid breakaway point or invalid. So we have two things: valid breakaway point, let me call it as BAP, and invalid breakaway point. So I will make you understand these two things, what is which we call it as valid and invalid breakaway points. Let me see here. If the value of k is positive, let me change the ink color. If the value of k is positive, then that breakaway point is valid for the root locus. Means if I value of k, whatever the value of k, if it is positive, then it is valid breakaway point. Then if value of k is negative, then it is invalid breakaway point. This is one thing. Just by finding out the value of k, we can tell. Means if I will substitute the value of s here, if I get the value of k as positive, then I'll treat it as valid breakaway point. If I get the value of k as negative, it is invalid breakaway point for direct root locus. I already told what is direct root locus and indirect root. Indirect root locus, value of k is varied from 0 to infinity. Indirect root locus we are not seeing, leave it, right? Okay. So we'll take this numerical. For g of s into h of s is equal to k divided by s into s plus 1, s plus 4. Determine the coordinates of valid breakaway points. Okay, we'll see this. G of s into h of s is equal to k divided by s into s plus 1 into s plus 4, and they are asking to find out valid breakaway point. Valid breakaway point. We have to find out this. Okay, fine. So first form the characteristic equation. Characteristic equation: 1 plus g of s into h of s equal to 0. So 1 plus, what is g of s into h of s? It is k divided by s into s plus 1 into s plus 4 equal to 0. So solving this, we will get the third order equation. Let me directly write here by looking at this: s cube plus 5s square, s cube plus 5s square plus 4s plus k. Okay, after solving this, I will get the third order equation, right? Take LCM, I will do simplification. So I will be getting the third order equation: s cube plus 5s square plus 4s plus k equal to 0. Next, we have to separate out k terms one side and s terms one side. So we'll separate. K is equal to, send all these s terms on that side. K is equal to minus s cube minus 5s square minus 4s, right? Then I have to differentiate k with respect to s. This is because we know that dk by ds equal to 0, right? So we will equate dk by ds with respect to s. I have to differentiate and equate it to 0. So minus nx to the power of n minus 1, right? 3, right? Nx to the power of n minus 1 minus 5 to the 10s, right? Is it fine? Minus 4. I hope it is correct, right? So it's correct, right? Differentiate with respect to s, minus nx to the power of n minus 1 by 2 is 10, yes, and this is s, right? Minus 4, it's correct. And equate this to 0. So all are minus sign, so multiply throughout by minus 1. So I will be getting equation 3s square plus 10s plus 4 equal to 0. So solve this quadratic equation. That roots will give me the valid breakaway point, which is valid, that we will see, right? So I will go to equation. Degree is 2. So a value is 3 here, b value is 10, c value is 4. So I got the equation breakaway point as s equal to minus 0.464. This is one breakaway point, and another one I am getting it as comma minus 2.868. So we got these two breakaway points. BAPs. So which one is valid? So I have to find out which one is valid. There are two ways of finding valid, which is valid breakaway point. First, I will draw the uh, pole 0 plot, part of root locus, right? So just s equal to 0, one of the pole is located. S equal to -1 and -4, -1 and -4. Okay, poles are located, no zeros are there. Then I will tell on where the root locus exists. Let me change the ink color. Yes, whether root locus exists between 0 to -1, yes, because it is odd, so root locus exists here. From -1 to -4, no root locus because even number. From -4 to -infinity, yes, root locus exists here because if I take 1 point, 1, 2, 3, odd. So root locus exists from -4 to -infinity, then it is from 0 to -1. Then next, we know the general predictions where the breakaway point exists. Since these two are adjacently placed poles, one minimum breakaway point exists here, right? One minimum, one BAP. These two, -1 and -4, they are adjacently placed poles, but there is no root locus here. So leave it. And this here, if it is root locus also, there is no breakaway. So breakaway point exists in the section 0 to -1. So just check the value. So 0 to -1 means this -0.464 lies between 0 to -1. But whereas this -2.86 somewhere it will come here. So this is invalid. So this is valid. And this one is invalid. This is one way of telling, right? So this is valid breakaway point and this is invalid breakaway point, right? Just by looking at this diagram, right? So it is better to look at the diagram and tell you. Another way is, yes, by finding out the value of k. What is this value? Call this as equation 1. Substitute the value of s here in this cubic equation, right? I will substitute -0.464 here in this equation. If I get the value of k is positive, then it is valid breakaway point. I will not do it. Just substitute this value -2.868 in equation 1 here. If I get value of k as negative, then it is invalid BAP. Right? So this is another way. Just substitute the values of s, whatever you've got breakaway points. So if I substitute -0.464, I will get value of k as positive. So it is valid breakaway point. If I substitute k equal to negative value, so -2.868 in equation 1, I will get k value as negative. So it is invalid. So this is invalid breakaway point and this is valid breakaway point. So s equal to -0.464 is valid breakaway point. I hope you got it. If any doubts, you can ask. There are two ways of finding out valid breakaway point, right? Just better to go for diagram. Then rule number 6 is over. It had spoken about the breakaway points. Next, we will see. Okay, 1 minute. I'll change the calci. Okay. Okay, rule number 7. Yes, rule number 7 will tell us the intersection of root locus with imaginary axis, whether the root locus will intersect with imaginary axis or not. That's all it will tell. And how it can be determined, that intersection points. Let me take one example of root locus here. We can see this root locus. See here, root locus will move and it is intersecting here on the imaginary axis, here and here, right? So here it is plus j 1.732, here minus j 1.732. So where it intersects on the imaginary axis, that is given by rule number 7. Rule number 7 speaks about this. Rule number 7 tells whether the root locus will intersect with imaginary axis and which are these points. How to find out these points, right? How to find out these points. That is rule number 7. That we'll see how, right? I hope you understood, right? We'll see how to find out the intersection points. Consider the characteristic equation. Step 1. Consider the characteristic equation 1 plus g of s into h of s equal to 0. Then construct root array. You know how to, once characteristic equation is ready, you know how to construct root array in terms of k. And determine the k marginal value. How to determine k marginal value? One of the rows should be entire, means I should get row of zeros. So you substitute, make one of the, substitute the value of k in such a way that one of the row will become 0, except that s power 0 row, right? S power 0 row is a constant where I will get, right? So that marginal value of k, which creates one row as row of zeros. Just above the row of zeros, you know how to form the auxiliary polynomial. In the previous chapter we have seen, right? What is the
Excuse me,
alternative?
sir.
Yes, tell me.
So your screen has been stopped presenting, sir.
Skin has been sure for others.
Yes, sir. Present your screen, sir.
Presenter screen. 1 minute. Now it has happened or long back?
Just now, sir.
Okay, once again let me check it. I will just 1 minute. Keep this. Oh, 1 minute. Voice says okay. Once again, I don't know what happened, but net connection is there. Let me check it. 1 minute. I'll share. Wait. Internet off ಆಗಿಲ್ಲಲ್ಲ? ಇರ್ಲಿ. 1 minute. I'm sharing. I don't know automatically why it had happened. Your entire screen. Share. Now it is visible.
Yes, sir.
Okay. I hope till rule number 6 everything is clear. Shall I proceed with rule number 7?
Yes, sir.
Okay, fine. Just now your rule number 6 is finished. Rule number 7. Yes, just we will have how to find out the whether the root locus is intersecting with imaginary axis or not. Means we want to find out these points. So here for this example it is plus j 1.732 and minus j 1.7. How to find out this? Next we'll see the steps. How to find out these intersection points of root locus with imaginary axis. So first step is consider the characteristic equation 1 plus g of s into h of s equal to 0. Yes. Then construct the root array in terms of k. Yes. And we'll determine the marginal value of k. Marginal value of k means one of the row, entire row should become 0. Yes, if the entire row becomes 0, means what is the indication? It is indication of presence of pair of symmetrically located roots. Here those pair of symmetrically located roots are nothing but the imaginary axis, the roots located on imaginary axis here in this rule number 7, right? And we'll know how to construct the auxiliary equation, right, by using the coefficients of error just above the row of zeros. This we have seen in the previous chapter. Then find out the roots of auxiliary equation by for k marginal value, for k equal to k marginal value, that will give us the intersection points. So okay, these are the rules, and we'll solve one numerical based on this so that you will understand how to find out the intersection points, these intersection points. These intersection, how to find out, you will come to know. We'll see. We'll take up this example. Consider g of s into h of s is equal to k divided by s into s plus 1 into s plus 4. Find the intersection of root locus with imaginary axis. Okay, we'll find out. G of s into h of s is equal to k divided by s into s plus 1 into s plus 4. Yes, we'll find out the intersection point with imaginary axis. Intersection points of root locus with imaginary axis. So first step, find out the characteristic equation. 1 plus g of s into h of s equal to 0. So 1 plus g of s into h of s is nothing but k divided by s into s plus 1 into s plus 4 equal to 0. So after solving this, I will get the third order equation, this one. So I will just take down this s cube plus 5s square, s cube plus 5s square plus 4s plus k. So you know how to take LCM, and you will get the third order equation, s cube plus 5s square plus 4s plus k equal to 0. This is the characteristic equation. Next, form the root array or root table. Form the root array or root table. So all the powers of s are present, s cube, s square, s power 1, s power 0. Form, you know how to form it. So list out the odd term coefficients 1, 4. 1 and 4. List out the even term coefficients 5 and k. 5 and K is the constant term. So I'll mark it like this. Okay, next, only one element here. How to calculate 5 4 is 20 minus 1 into K divided by 5. Only one element, and this is the constant. So one of the row, entire row should, this row cannot be 0, this row cannot be 0, but I can make this as row of zeros. Row of zeros. By substituting that particular value of K. If K is 20, right? If so, what I will do? Marginal value of K I will call it as K equal to K marginal. That marginal value of K is, let me write KAMAR, that's all. My MARGIN, I will not write K marginal. If I substitute K equal to 20, this will become 0, right? So it is 20. So this I will call it as marginal value of K, so that the entire row becomes 0. But don't substitute K equal to 0 for the constant row, right? Leaving this constant row, any other rows should become 0. So this row will become 0. So next, just above the row of zeros, we will form auxiliary polynomial A of S. Just above row of zeros means this one, right? 5s square plus K into S power 0 equated to 0. But what is substitute K equal to K marginal? What is this? Substitute K is nothing but K marginal here. So I'll substitute this K value as 20. 5s square plus 20 equal to 0. So 5s square equal to minus 20 by 5. Yes. So minus 4. So S equal to, what I will be getting? Plus or minus J2. Is it fine? Yes. So I'll be getting S equal to plus or minus J2. So we came to know that these are the intersection points of the root locus with imaginary axis. So it will intersect at plus J2 and minus J2. The root locus will intersect at sigma j omega. It will intersect at plus J2 and minus J2. Here, let me show you in this example. It will come here and it will intersect here. This is plus J2. Simply example I am telling. This branch will intersect here minus J2, for example. That's all, right? Okay. I hope you understood how to find out the intersection points of root locus with imaginary axis, right? First, form the characteristic equation, form the root array, make one of the row as row of zeros by suitable value of K, right? That is K marginal value. Form the auxiliary polynomial, solve the roots of auxiliary polynomial by substituting K marginal value of K. You will get the intersection points. Rule number 7 is over. Then rule number 8. Okay, most of the times we will not be using this rule number 8. Yes, we will be using, but right now we are not using, because whenever there are complex conjugate poles and complex conjugate zeros in the given open loop transfer function, then only this rule number 8 is applicable, or else it is not. For example, if the open loop transfer function is this, if the open loop transfer function is this, g of s into h of s is equal to k divided by s into s plus 1 s minus 4, there are no zeros. Poles are located at 0, minus 1, minus 4. Are there any complex conjugate poles here? No. If there are only complex conjugate poles or complex conjugate zeros, then only rule number 8 is applicable. Or else we can skip that rule number 8 while drawing the root locus, right? So, okay, yeah, let me assume that there are complex conjugate poles and zeros. So, angle of rule number 8, angle of departure at complex conjugate poles and angle of arrival at complex conjugate zeros. So I will make you understand. Let me take this example. Yes, let me take this example, right? This is one root locus. Don't worry, just the diagram is like this. This is one complex conjugate pole, minus 2 plus J3. Yes, it is located here. Next, minus 2 minus J3. It is located here. Yes, complex conjugate pole is there, right? So always the branches will leave the pole, right? It can leave in different directions. Here, if I will change the ink color, it may leave like this, it may leave like this. But how it should leave? That is where how with here in this example you can see here the angle of departure always it is minus 33.69. So this angle is minus 33.69 degree, means the pole, the branch will leave like this. It will leave like this. Then this asymptote will tell me move parallelly with me. So it will move parallelly with me. So initially, how it should leave, how it should depart, at what angle? It should depart at an angle of minus 30. How to find out this departure angle? Here it is phi d. If it is complex conjugate pole, if it is complex conjugate 0, instead of pole, suppose there is 0, so angle of arrival we will call it as. Always the branches will leave the pole, always the branches will enter the zeros. So Whenever there is a pole, complex conjugate pole, I will call it as angle of departure because it is living, the living. Whenever there is a complex conjugate 0, I will call it as angle of arrival. It should come to the 0 here. Always from pole it should leave. For 0 it should come. Pole is here, the branch will leave. 0 is here, the branch will enter direction. I hope you understand. So hence we call it as angle of arrival for the complex conjugate 0 and angle of departure for the complex conjugate pole. Here and for the complex conjugate pole, the angle of departure is minus 33.69 at minus 2 plus j3. You can see due to symmetry, minus 2 minus j3, angle of departure here it is plus 33 point. This should be exactly opposite. If it is minus 33.69, it should be plus 33.69. So I will calculate only the angle of departure for only one point, minus 2 plus j3. It is exactly opposite for minus 2 minus j3, right? So how to calculate this angle of departure and angle of arrival, that I will take now. Is it fine? Okay, we'll see. Yes, the formula. So how to calculate the angle of departure? The formula is, just 1 minute. Where is the pointer? Yes. Okay. So formula is given by angle of departure is 180 degree minus phi for angle of departure for complex conjugate poles, right? So 180 degree minus phi. For angle of arrival, if there is, so it is 180 degree plus phi. How to remember whether it is plus or minus? Departure means leaving, so it is minus 180 degree minus phi. Arriving means 180 degree plus phi plus. I hope you are getting. So for departure it is 180 degree minus phi. For arrival it is 180 degree plus phi. Then how to calculate this value of phi? It is same in both the cases. Whether I calculate angle of departure phi d. So phi d we call it as angle of departure. Angle of arrival phi a. A stands for arrival, D for departure. Angle of departure, angle of arrival. So how to calculate this angle of phi? It is phi is equal to sum of all the angles subtended by the remaining poles minus sum of all the angles subtended by remaining zeros. Here also it is same thing. Phi is sum of all the angles subtended by remaining poles minus sum of all the angles subtended. You will not understand anything if I say like this, right? So just we'll solve one numerical. Based on this, you will come to know what is this angle subtended by other poles and what is the angle subtended by other zeros, right? You will understand that. Right now, so you remember these two formulas. Angle of departure is 180 degree minus phi, and phi is summation of phi p minus summation of phi z. And angle of arrival is 180 degree plus phi. Phi is same in both the cases. I hope, right? We'll see it. Next. Okay, I'll take up this example. How to calculate determine the departure and arrival angles. Departure angle for poles, departure angle for complex conjugate poles, complex conjugate poles, and arrival angle. This arrival angle is for complex conjugate zeros. Complex conjugate zeros, right? So calculate the departure and arrival angles at complex conjugate poles and zeros for g of s and h of s equal to k into s square. Okay, we'll take up this. Okay, this solution is there. I'll not go through the solution. Let me take up in the new slide. Yes, the same thing has been taken here. Determine the angle of departure and okay, fine. First, we'll calculate the angle of departure. So before that, how many poles and zeros? We'll list it out. How many poles are there? Just look at the denominator. 1, highest power of s, 2, 3, 4. 4 poles are there. Where they are located? They are located at s equal to 0, minus 2. And what we have to solve the roots of this? S square plus 2s plus 101. So the root, let me have a look at it here. Minus 1 plus or minus j10. Minus 1 plus or minus j10. Minus 1 plus j10 minus 1 minus j10. Okay, solve the roots of this s square. So already instead of solving, just I had a reference there. So I have taken the roots of this s square plus 2s plus 101 is minus 1 plus j10 minus 1 minus j10. 4 roots are there. How many zeros are there? Observe, yes, 2 zeros are there because in the numerator highest power of s is 2. So let me have a roots of this also. Solve the roots of this s square plus 3s plus 10. You can use calculator or else just I have the reference here. Let me take it here. S square plus zeros where they are located here. Yes, the zeros are minus 1.5 plus j 2.78. Minus 1.5 plus j 2.78. Right? Okay. Sorry, another is minus 1.5 minus j 2.78 plus or minus, right? 2 zeros are there. Okay, so since yes, I have, let me change the ink color. I have complex conjugate pole -1 plus J10 and -1 minus J. So I will calculate angle of departure for this. And the formula is 180 degree minus phi. Then since there is complex conjugate 0, -1.5 plus J and -1, these are complex conjugate zeros. So I will calculate angle of arrival phi A. And formula is arrival is plus, this is minus. So arrival means plus phi. Then how to calculate this value of phi? Phi is the sum of the angles subtended by the remaining poles minus sum of the angles subtended by remaining zeros. What is this? I will make you understand. You try to remember this formula, right? So first we'll calculate phi d, then phi a will say. First we'll concentrate on calculation of angle of departure. Calculation of angle of departure. Angle of departure phi d at which point? So let me take this point -1 plus J10. I will not take this because if I calculate at one point it will be exactly opposite. So at -1 plus J10. -1 minus J10, no need to calculate, it will be opposite. So calculate the angle of departure phi d at this point -1 plus J10. Okay, so we will locate all the roots, everything. Draw the pole zero plot. Sigma j omega. So the poles are located at 0, -1 plus J10. This is -1 plus J10, somewhere it will come here, right? So it is plus J10 and this is -1. So here minus J10, right? So this is over. -2, one of the pole is there, -2. Okay. Next, we will look at the zeros. -1.5. Somewhere it will come here, -1.5, right? Let me use some other ink. -1.5 plus J 2.73 means somewhere it will come here. So the diagram was very, I should have taken big, expanded this. Let it be, no problem. Okay, this is plus J 2.78. Here, let me take it. Corresponding to this is minus J 2.78. Okay, I have located all the poles and zeros. I have not left anything, right? Okay, next we will consider, we will calculate angle of departure at -1 plus J10. This is -1 plus J10. This one, right? This one. So this is the point under consideration. So from remaining poles and zeros, first I will take the poles. So this is the first pole. Let me join the line from this first pole. So angle subtended by this first pole, let me call it as phi P1. Angle subtended by this pole. This is the first, I will call this as first pole. So angle subtended first pole is phi P1. Then second pole is here. So let me draw this line here like this. So the angle subtended by the second pole is phi P2. Right? The next third pole is here. Sorry, I have made mistake. Nobody has told. What is that mistake? Can you tell anyone what mistake I have made? I have made some mistake while drawing the diagram. If you are attentive, you will tell, sure. That is for sure. What mistake I have done?
Zero.
Yes, while locating zeros, I have used the pole symbol. Right? It should be 0, right? So let me change it. Yes, good. This is 0, not pole. Yes, 0. Yes, this mistake. But you please, you tell me if I make mistake, right? Okay, let me change the ink color. Okay, first pole is over, second pole. Third pole is here. So let me join from this third pole. So this angle subtended, let me call it as phi P3. I hope you got it. So how to calculate this phi P value, you came to know. Phi P1 plus phi P2, phi plus phi P3, summation of phi P. Then similarly zeros. So this 0 is located here. From this 0 you join it, right? So let me change some other ink color, or else, okay, let me redraw it because this is very cumbersome. I think this is not possible if I proceed like this. So let me redraw it. sigma j omega. At 0 one of the pole is located, fine. 0 minus 1 plus j10. Let me take it somewhere here, plus j10 plus j10, and here let me expand this, minus j10, right? Minus 1 plus j10. Then next another at minus 2. Let me take this minus 2 here somewhere at far, so that it will be easy for me. And minus 1.5 somewhere I'll take here, minus 1.5. okay, poles are fine. 0, this pole fine, this is fine. Then plus j 2.78. so let me take this minus 2.78 right here. Corresponding to it is plus j 2.78, another 0, minus j 2.78. okay, next this is minus 1 plus j10. so let me change the ink color from first pole. Let me take this join from first pole to this. Okay, let it. This angle is 5p1. Second pole is here. Second pole is here. This angle is 5p2. Then third pole is here. So this angle is 5p3. By trigonometry, using the trigonometric rules, geometric rules, we will find out 5p1, 5p2, 5 by geometry we will find out. Then next, yes, angle subtend poles, but angle subtend by zeros. So let me take this 0, right? So let me change the ink color here. Let me take it orange from here, right? So I'll join this. So angle subtended, this angle we call it as, this is the first 0, phi z1, right? Then the second 0 is here. So let me join it here. So let me join it and make it triangle, so that right angle triangle. So similarly, let me make it right angle triangle for this also. This angle is phi z2. So angle subtended by zeros. I hope you got it, right? So we'll calculate angle of departure first. So yes, what is 5p1? How to find out? You'll see how to calculate 5p1. So let me write it here only, 5p1. So let me change in color and write it. 5p1. How to calculate it? By looking, you come to know that 90 degree plus something, right? So 90 degree plus something. So it is between 90 to 180. It is for sure the angles of 5p1 should be 90 to 180. So what we will do? So this is the triangle. You can observe here this right angle triangle. I can observe here this is the right angled triangle and this is the right angle, right? So I want to find out this angle. 180 degree minus this will give me this, right? So 180 degree, this is the angle, minus this angle. So I will make use of 180 degree minus tan inverse of this angle. I want to calculate 180 degree minus this angle, that will give me 5p1, right? So you can do it in any way you want. So 180 degree minus tan inverse of this angle, opposite by adjacent. Opposite means this one. So how much is the height? 10. This height is 10, right? From here to here. So tan inverse of 10, opposite by adjacent. Here it is 1. 1 is, so 10 by 1. So we will calculate this. If any doubts, you can ask. This is geometry, that's all pure geometry. 180 degree minus tan inverse of 10. So I am getting it as 95.71 degree. So this angle, it is correct. It is between 90 to 180. Next, calculate 5p. No need to calculate because it is perpendicular. So it is 5p2 is, because we are measuring the angle in anti-clockwise direction. So 5p2 is plus 90 degree. Plus 90 degree. It is not minus because it is measured in anti-clockwise direction. So 5p2 is 90. Then 5p3. How to calculate 5p3? Okay, this is the triangle, right angle triangle, big triangle, right? This is 90 degree. So you know the tan inverse of opposite by adjacent. So opposite is 10 and adjacent this here 2 to 1. 2 minus 1 is 1, right? So minus 2 minus 1. Totally I want only magnitude, right? So this 2 minus 1 is 1. So tan inverse of 10. So tan inverse of 10. So I am getting 84. 84.28 degree. So I calculated 5p1, 5p2, 5p3. Similarly, you calculate 5z1 and 5z2. If any doubts, please let me know. 5z1. Okay, still time is there. I will finish this at least calculate angle of departure at least today. 5z1, how to calculate? This is triangle. Observe here, this is the right angle triangle. So tan inverse of opposite by adjacent, opposite this height from here to here. 10, this is 10, 10 minus 2.78. Tan inverse of 10 minus 2.78. This height from here to here. This is 10, here it is 2.7. So subtract. So you will get this height divided by opposite by adjacent from here to here. So 1.5 minus 1. 1.5 minus 1 here. Right? So it is 0.5. So we'll calculate this 5z1. So shift tan inverse of, so 10 minus, okay, let me divide this. 10 minus 5.2.78. So I am getting 7.22 divided by 0.5. And we'll calculate tan inverse of this. Tan inverse of this answer 14.44. So I am getting it as 86. So here I am getting it as 86.03 degree. Next, similarly, you calculate 5z2. 5z2, this is the triangle, right angle triangle, big one, right? So tan inverse of opposite by adjacent. So opposite means this. Say from here to here it is 10. 10 plus 2.78. So it is 12.78. Right? 10 plus 2, this height. And here 1.5 minus 1. So it is 0.5. So we'll calculate this. Shift tan inverse of 12.78 divided by 0.5. So I'm getting 87.75 degree. Okay, we have calculated all these angles subtended by remaining poles and zeros. Next, we'll apply the formula. Angle of departure phi d is equal to 180 degree minus phi. So call this as equation 1. And we know that phi is nothing but the sum of all the angles subtended by the poles minus sum of all the angles subtended by zeros. Okay, we call this as equation 2. So first, find out summation phi p. Phi p is equal to summation of phi p is equal to phi p1 plus phi p2 plus phi p3. So add all this, phi p1 plus phi p2 in the previous slides. Here I have phi p1, so 95.71 plus phi p2 is 90 degree plus 90, phi p3 is 84.28. 84.28. So I got it as, let me write it here, 269.99 degree. Then let me calculate summation of the so angle subtended by 0, summation of phi z. It is phi z1 plus phi z2. So we'll add this. Phi z1 is 86.03 plus phi z2 is 87.75. 87.75. So I got it as 173 after adding 173.78 degree. So we will calculate phi from equation 2. Equation 2 implies phi is equal to summation of phi p 269, phi p minus this 269.99 minus 173, right? So 269.99 minus 173.78. So I am getting 96.21. So substitute this value of phi in equation 1. So equation 1 implies angle of departure phi d is equal to 180 degree minus phi. Phi is 96 point, so 96.21. So calculate this, 180 degree minus 96.21. So I am getting it as 83.79 degree. So this is the angle of departure. Angle of departure what we have calculated is 83.79 degree at which point? At this minus 1 plus j10. At minus 1 plus j10. So what about the angle of departure at this minus 1 minus j10? So it is exactly opposite. So angle of departure is, just if it is plus means here it is minus 83.79 degree. Okay, let me finish off this. Time is up. At minus 1 minus J10. I hope you got it. Angle of departure, right? So at this point, so how it will live? Let me draw the diagram here. 83.79. So here I will measure the angle here. So 83.79 means somewhere it will come like this. Means the branch will leave like this somewhere, and later on it is decided by asymptotes. Here at this point minus 83. Minus 83 means the branch will leave like this. The minus 83 means it will come like this. The branch will leave somewhere like this, right? Symmetry should be there. I hope you understood how to calculate angle of departure. Angle of arrival I will take in the next class. I will stop the lecture here.